Alright, let's do a question which will help you understand how to build a solution from the most inefficient solution to the most efficient solution. This question is a very interesting one because it helped me understand how to build the more efficient solutions as in when you're trying to optimize your algorithm, right? So the question is grumpy bookstore owner. It says that so you have a bookstore with customers array and a grumpy array. So the customers array specifies that what is the satisfaction the customer gets at that particular minute, and the grumpy array specifies of when the bookstore owner is grumpy. So whenever he's grumpy, um, the customer's satisfaction in whatever values on this array is gonna go down to 0, right? And the other catch of this question is that for approximately x number of minutes you can say that you can force the bookstore owner is to not be grumpy, like give him a drink or something like that. That's how, and we are supposed to compute the maximum satisfaction we can get. So the moment this question comes, the first thing I think of is uh, how it's a greedy algorithm that I'll have to apply. So I would want to just try and find the all the solutions and compute the maximum of those, right? Not exactly greedy, but yeah. So the first solution we will come up with is right. So in this particular question, x is equal to 3, correct? So the optimal answer is here. So we are going to try all of the solutions, right? We're going to say for the first interval from this start to this end, let's assume that the bookstore owner is not grumpy. So we are totaling everything, right? So it will be 1 plus 1 plus, this will not be included because it's against, here he's grumpy here, plus 1 plus he's not included again, 7 plus 5, this is equal to 15. Yeah, so this is equal to 15. The optimal solution, let's just compute that for example. So we are saying he's not grumpy at this particular index, right? So it will be 1 plus 1 plus 2 is not included again, plus 1 plus 1 plus 7 plus 5. So this is 4 plus 7, 11 plus 5 equal to 16. So we see this is the most optimal solution. We could compute all of them and compare, but let's just assume this is the most optimal solution. So our algorithm is the kind which tests for all the cases, right? So our start index is 0 and end index is x start plus x minus 1. It's a 0 indexed array, so that's the minus 1, and till we reach an end index of the end pointer reaches the end index, we're not going to stop the while loop. And this inner loop basically just sums everything up and ignores all the ones. If it's 1 or if it's out of range, we're going to ignore it, or else we're just going to add it to the satisfaction. This one checks for the global satisfaction. These two just move it around, move the start and the end pointer. Now the time complexity here is O of n is the time it takes for us to go from start to end, right? And we are going to have the start and the end pointers keep moving, and that's going to move how many times into n minus x plus 1, right? So this one is approximately an O of n square algorithm, which is good but not the most efficient. How do we reduce the time complexity here? Now the next solution that kind of comes to my head is a case kind of a solution, like I am assuming that x is uh, usually lesser than n. So what we can do is we can compute the entire sum with taking the grumpy indexes, and then try to do our start and end pointers stuff, right? So what I mean by that is, let's say I'm going to compute the entire sum here, which is going to be 1 plus 1, this 2 will be ignored, plus 1 is 3, this 1 will be ignored, plus 7, and this 5 will be ignored. So this is 10. Now I'm going to say between this start and end, the owner is not grumpy. So I'm going to see if anything was 1 and I left it out in my initial computation and add it to that global sum, right? So first my start and end is here, so I'm going to go through this entire thing. Okay, there was a 1 here, add the 0 to that. 10 plus 0 is 10, so which is of no change for us. Then I take my start and end indexes, then I take my start index and my end index and move it again, right? And I'm going to see if there is anything that I missed, right? So yeah, the 2 is what I missed because of grumpy, but I'm assuming that he's not grumpy right now. So 12 is greater than the previous computed one, so 12 is our current maximum value. Remember to add this to the 10 always and not to the previous maximum value, right? Next I'm going to have my start and index, end index move again, right? Start and end. Here it's going to be 10 plus 0 again, so that's 10. And similarly, when we reach the end of this, right, it's going to be 10 plus, we missed this one, plus 5, which is 16, which will give us our maximum value. Now this is the other algorithm. This would be kind of helpful in the case where x is smaller, right? X is a small value, because if I have O of n plus, I'm going to say I'm going to compute x how many number of times. I'm going to compute the sum of, go through 0 to x, so that x into start to end is basically the range, that is n minus x plus 1, since it's a 1 index 0, so x into n minus x plus 1, which is nx minus x square plus x, right? So we do see this is still might be better for, you know, small values of x, but larger values of x might not really help in our case. Right, so that x is being computed how many number of times, let me just see, this looks a little incorrect. That x will be computed in our this case will be 1 time, 2 time, 3 time, 4 time, 5 time, and 6 times, right? So 6 would actually be n, that is 6 minus 3 plus 1. Yeah, right. So this is, yeah, we're doing slightly better, because this looks a little better than order of n square what we got in our previous algorithm. Now we are going to try the most efficient solution, which would be around order of n. And how do we do that, right? If you observe something, we do not need to, in the previous solution, why I specified that even though it's kind of order of n square in certain cases, why I specified that solution was we can move this window, right, rather than having to compute everything within it. We can subtract this by a small programming trick. We can subtract this and add this. So what I mean by that is, again, what we will try to do is compute everything. So like in the previous example, that was 10. Now I will compute the first one, and I will see that, okay, from this 10, from the initial value 10 in this window, is there any value that I can add? Yes, it's 0, so that will be 10. Then I'm going to move my start and end pointers, start and end. I'm going to see if start minus 1 was a 1. If that was a 1, I need to subtract that from my satisfaction, right? From my previous satisfaction, right? So if you, what I mean is, if it was 1, so I need to subtract it, and if the new has been 1, I need to add it to my satisfaction, right? So what I mean by that is, so if it was 10 total, so my previous satisfaction was 0, so no changes here. Then it was then I move the start and the end pointer, so the new end has 12 2 included in it, so 10 plus 2 is 12, right? Then the new start is here and the new end is here, right? And I'm going to say did the previous one have anything, so I'm going to say 10 minus 0 sorry 12 minus 0 is 12, and my new end pointer has a 0 index grumpy, so it's fine. It's not, I'm not just ignoring it again, there's no value change there. And then again I move my start index to this and end index to this, which will be 12. There was no changes here, but I can add this new one because this index is safe. So 12 plus 1 is 13. Then again I'm going to move my start index and end index. I'm going to see if the start minus 1, the previous start index, if it was a 1, I need to subtract the value, and if the new end index is a 1, I need to add that value, right? So then in the we are here, right? So this is the new start and this is the new end. And is there anything new? Yeah, we need to exclude this value, so we're going to say 13 minus 2 is equal to 11, right? Then I'm going to move my start and end index again, start and end, right? And is there a new value to include? Yes, this 5 is a new value to include, the end is added, so 11 plus 5, again we reached our 16. This algorithm would be okay, order of n, to compute the entire thing. And since we are not having an inner loop and we are just going to compute the sums here, just add and subtract this, we just need to compute the number of times this window was moving. So in this particular case it was 6, which is again n minus x plus 1. So if we see order of n plus n minus x plus 1, which is order of 2n minus x plus 1, which is close to order, which can be order of n theta of, right? So we reached an order of n algorithm by just changing small values. So this is how an expectation would be in any kind of programming interview, to be able to build efficient solutions from ground up. You start with the most inefficient one and you keep moving up from there. All right, just